There are these invisible forces all around us all the time. Forces that can do some pretty wild things. They can pin you to the ground, or, if you know the secret, they can give you almost superhuman strength. Today, we're going to pull back the curtain on one of the most important of these forces, pressure. So, let's start with a puzzle. How in the world can your foot, with just one little push, stop a 2-ton car in its tracks? I mean, it sounds completely impossible, right? But it's not magic, it's physics. And by the time we're done here, you're going to know exactly how it's done. All right, to solve this mystery, we've got to get a handle on 2 key ideas first: thrust and pressure. Now, you might think they're kind of the same thing, but in the world of physics, they are totally different. Okay, so first up is thrust. This one's pretty simple. Imagine you're just pushing against a wall. That entire force you're putting into it, the whole oomph, that's the thrust. It's the total push. But now we get to pressure, and this is where things get really cool. See, pressure isn't about the total push. It's about how concentrated that push is. It's the same force, but squished into a certain area. You can think of it as the sharpness of the push. So let's break it down side by side. Thrust is the grand total of the force, but pressure, that's the force per unit of area. Think about walking on soft sand. You sank, right? But what happens if you lie down? You don't sink anymore. Your weight, the thrust, is exactly the same. The only thing that changed is you spread that thrust over a much bigger area, which totally dropped the pressure. And that idea right there, being able to spread a force out or focus it down to a tiny point, that's the secret sauce. By playing with that relationship, we can do some absolutely incredible things. It really is all about the power of the point. And here is the magic formula that runs the whole show. Pressure equals thrust divided by area. It's so simple, but it's the key to everything. What this tells us is that for the very same amount of thrust, if you can make the area smaller, the pressure goes through the roof. And this is a perfect example. Just look at the brick. On the left, it's lying flat. Its weight is spread out over a big surface, so the pressure is pretty low. But now look at the right. It's the exact same brick, with the exact same weight, but it's standing on its end. All that thrust is now focused on one tiny little spot. And the result? Way more pressure. And we use this trick all the time, everywhere. Think about it. We make knives super sharp and nails pointy. Why? To create massive pressure so they can cut and pierce without a lot of effort. And then we do the exact opposite when we want to decrease pressure. That's why snowshoes are so big, to spread out your weight so you can walk on top of the snow. It's also why train tracks sit on those wide wooden beams, to spread the incredible weight of a train across the ground. Okay, so that's how it works for solids like bricks and nails. Pretty straightforward. But what about things that aren't solid? Things that flow, like water, or even the air around us. Well, it turns out the same rules apply, but with a really fascinating new twist. And check this out. This shows the twist perfectly. See how the water jet shooting out of the lowest hole is the strongest? It travels way farther. That's because the deeper you go in any fluid, the more stuff is on top of you, weighing you down. More depth equals more weight, and more weight means more pressure. Now, this isn't just some cool little science experiment. It has huge, real-world consequences. Just look at this dam. You see how it's crazy thick at the bottom and gets thinner as it goes up? That's because it has to be. The pressure from all that deep water at the bottom is just enormous. If it wasn't built that way, the dam would just burst. So we know pressure is a big deal in liquids, and it gets stronger the deeper you go. But back in the 17th century, this brilliant guy, Blaise Pascal, he figured something else out about fluid pressure. Something so powerful, it became the foundation for almost all modern hydraulic technology. And this is it, Pascal's law. It sounds a little formal, but what it means is actually pretty simple. If you have a liquid sealed up in a container and you apply pressure to it, that pressure doesn't just stay in one spot. It instantly spreads out equally to every single part of that liquid. This flask here shows it perfectly. When you push down on that piston at the top, watch what happens. The water doesn't just squirt out of one hole. Nope. It shoots out of all the holes at the same time with the same force. A push in one place creates an equal push everywhere else inside. And right here, this is the mind-blowing part. If a push in one spot becomes an equal push everywhere, and if we can change the size of the surface that push is acting on, well, what does that mean? It means we can literally multiply force. Which, of course, brings us all the way back to our original question. how do we take this incredible principle and actually use it to stop a 2-ton car? It's time to put all the pieces of the puzzle together. So how do we do it? Okay, picture this system. You apply just a little bit of force to that small piston on the left. That creates pressure in the fluid. Now, thanks to our friend Pascal, that exact same pressure travels everywhere and is now pushing up on that much, much bigger piston on the right. And since pressure acting on a bigger area creates a bigger force, your tiny little push just got multiplied into a huge lift. You've definitely seen this in real life with a hydraulic jack. You see someone making these small, easy pumps on a little lever, right? That's the small force on the small piston. That simple action generates an incredible amount of pressure, which then lifts a massive car like it's nothing. Tiny input, massive output. And that brings us to the final answer. Your car's brakes. They're a perfectly designed hydraulic system. When you step on that brake pedal, you're just pushing a tiny piston. That little push creates pressure in your brake fluid, which then travels out to much larger pistons at every single wheel. The force from your foot gets multiplied, clamping the brake pads with enough power to stop 2 tons of moving steel. So it's not the strength in your leg, it's the power of pressure. It's taking a small force, focusing it, transmitting it, and then multiplying it into a force big enough to win against a car's momentum. That is the power of physics. So, there you have it. We've unlocked the secret. Just by understanding this simple relationship between force, area, and a sealed-up fluid, we can become force multipliers. This exact idea is used in giant construction cranes, in factory machines, even in roller coasters. So I'll leave you with this question. Now that you know the secret, what would you build with it?